Hello, class. So let's look at the chapter 8, which is combined loadings. The objective of this chapter is to discuss different problems where you have combined loading. For example, when you have axial load, when you have torsion, when you have bending, when you have shear, all occurring simultaneously, what happens? That would be the objective of this chapter. So first of all, let's look at concepts like thin-walled pressure vessels. And after that, we will continue our discussion to various cases. Like, for example, if you see there is a gas storage facility, what is the maximum pressure that this gas storage facility can withstand? And additionally, we will look at what happens to systems where you have normal force. Remember, we have something called a normal. So you have sigma is equal to P over A. That means it's a normal stress, right? Similarly, you'll have shear stress, which is tau equal to VQ over IT. So sigma equal to P over A, and then you'd say tau is equal to VQ over IT. You must have you should remember this one because this is one of the latest topics, and this is something that we discussed in the class. Tau is equal to VQ over IT, and then bending moment, sigma is equal to negative my over I, right? This is stress due to bending moment. So this one is stress due to bending moment. This is stress due to shear force. This is stress due to normal force, right? What happens when you have a combination of all three? And similarly, we also forgot the fourth one is tau equal to torque times rho T rho over J. So if you remember, this is also one concept we discussed in the class in the previous chapters. So for instance, we will solve for a problem like this where you have a load acting not at the centroid but away from the centroid. There is an offset. When there is this offset, if you look at this picture, when there is this offset, what happens to this point C? That means what is the stress at point C? What is the stress at point B? You may think, oh, this is 15 kilonewton and it is compressing. It is a compressive force. So you may think C is also compression, which is true. What about B? Oh, 15 is trying to compress. So are you sure B will also be encountering a compressive force? Or because you see this 15 kilonewton, that is at an offset from this axis. Let me draw. So this is an axis, right? With respect to this axis, 15 kilonewton is at an offset by 50 millimeter. That means isn't 15 kilonewton causing a moment with respect to this axis? Let's say this is x-axis. So with respect to x-axis, isn't it causing a moment? It is. That means 15 kilonewton is just not a compressive force, but there is also a moment acting like that, which is being caused due to the 15 kilonewton force. So we have to also take that into effect. That means if you see this problem, isn't it a combination of a normal force, 15 kilonewton, which is basically this P over A, sigma equal to P over A, right? Isn't it sigma is equal to P over A? And isn't it also sigma equal to my over I? Isn't it both? It is both, right? It is both. So that is what we need to consider. Similarly, as we proceed further, so let me remove these two. We will see an effect caused due to this 15 kilonewton that is at an offset with respect to x-axis. Similarly, we will see something like this where you have this water in a water tank. What happens to A, point A? So presence of loading. So here there is pressure as well. From fluid mechanics course, there is pressure developed at A, and there is weight of this material. So if this material is made of, let's say, steel, this steel has some weight above this point A, and due to that weight, you have a force acting at A as well. So due to the weight of the steel and due to the water inside the tank, there is something happening to A. So we'll calculate that. And like a regular problem where we see, where you have this type of loading where you have A to B, you have an inclined load, inclined distributed load. Then if I ask you here, what is happening at C, where the cross section looks like this, that means you cut at C into the page, you see that it has a width 50 and it has a thickness 250 millimeters. And this C is here, you see, I'm exactly asking, I'm specifically asking you at that point, see what happens. So due to this distributed load, don't you have an equivalent load and don't you have supports? That's a statics problem. So from the supports, you make a cut at C. When you make a cut, you have to draw three things: normal, shear, moment. That means you have three things acting at C: normal, shear, moment. So due to these three, what happens to the point C? That is what we need to calculate. Similarly, this problem here. Look at this 40 kilonewton acting at a corner. Due to this, what happens to this point A, B, C, D? So these are some problems that we'll solve in this chapter. So with this introduction, let me introduce. So before I introduce a new concept, all these formulas that I have given you here, all these formulas that I have given you here, which is tau, which is sigma tau due to various loads. You already know all this stuff here. So if you look at this space here, sigma due to the normal, this is due to the normal, this is due to the shear, this is due to bending, this is due to torsion. We have seen all these four cases already. So this chapter is nothing new. It's just that when we combine all four into one problem, what happens? That's what we'll see. So before that, I have to introduce one concept, which is thin wall pressure vessels. So let's start from this concept.